Subscribe and order on netflix.com. India का ख्याल रखें, India की pharmacy.
Okay, guys, are you there? Guys, you there? Can we start now? Till 7. We'll have half an hour now. Because of power cut, we got disconnected. Okay. So we have discussed carbon family. We have discussed, like I said, the glass, anomalous behavior of carbon, allotropes of carbon. You'll go through, and there is one more thing. It is given in NCERT also. I realized this now. Silicates. Okay, you recall this now. Silicate and then structure of silicates. It is given in NCERT. Like for example, orthosilicates, pyrosilicates, cyclic structure or cyclic silicates, all these things are given. Basically the structure, silicates structure, it is given in NCERT. You just go through. Okay, in this only, when you see the structure there is one more thing that we call it as infinite chain silicates and then two-dimensional sheet silicates. So two-dimensional sheet silicates. Okay, so in this there are two types, right, which general form is Si2O5 N 2n minus. Similarly, we have the next one, which is three-dimensional sheet silicates. Okay, three-dimensional sheet silicates. This actually are of two types of three-dimensional, which is feldspar, and the second one is zeolite. Feldspar and zeolites. Now, what you have to memorize here, in feldspar there are orthoclase feldspar. Few examples are given like cesium, okay, arenathite, okay, like that. So, however, this feldspar example is not that much important, but zeolites also few properties which is given in NCERT and then few examples of it. Like we have gemelinite, edionite. These are the few examples of zeolite we have. So what are zeolites? Zeolites are basically these are the silicates of calcium, magnesium, sodium, all these, the complex structure of calcium, magnesium, sodium and all. That's we call it as zeolites. So there is a general formula of zeolites. Definition is also there, which is given in the book, that is NCERT, right? So these zeolites basically it acts as an ion exchanger. Okay. However, these things are not important. Okay. Just you when you go through once, you will understand. Okay. These things they don't ask generally, but a structure of silicates you must go through, which is given in NCRT, right? So these three, four things you have to read from NCRT. That's what I have said: glass, silicates, carbon, allotropes of carbon. That is it. Okay, which is we are left with in this particular um, you know chapter. Few compounds like carbon monoxide, carbon dioxide is also given in NCRT. That already you know it is not required. Okay, so now can we discuss a little bit about boron family? Okay, so we are starting with group 13, and that is boron family. So again, boron family will it's a small chapter, okay, but I don't think we will be able to finish it today, but we can finish by no next class. We'll finish on Saturday, and then we'll discuss some revision on Saturday also. It will take I think 1 or 1.5 hours or so, like that. Not more than 1.5 hour. I won't like take this so longer. 1.5 hour maximum. Okay. So whatever we can do, we'll do it today, and then we'll finish things in the next class, and then we'll start some equilibrium and all. If you want me to discuss some for exam point of view revision, right? You see, first of all, the atoms present in group 13 are boron, aluminium, gallium, indium, and then thallium. Atomic number, you see, for boron it is 5, then we'll add 8, so it is 13, 18, so 31, 49, and then 81. 8, 18, 18, 32 are the what we say magic number. Electronic configuration 1s2, 2s2, 2p1, or we can also write helium 2s2, 2p1. For this, it will be neon 3s2, 3p1, and here it will be argon 3d10, 4s2, 4p1, xenon, sorry, krypton. It is 3d10, sorry, 4d10, 5s2, 5p1, and this will be 4f14, 6d10, sorry, 4f14, 5d10, 6s2, 6p1. This is the electronic configuration. So the general electronic configuration here it will be what? It is ns2 np1. Okay. So quickly I'll go with the trends that we have. Okay, first of all, the atomic radius, if you see, atomic radius, I'll give you the value here. It does not follow a regular trend here. So I'll give you a value to make you understand. Boron, aluminium, gallium, indium, and thallium. These values is in picometer. 85, 143 increases and then decreases, then again increases, and then almost same, increase a little bit. Okay. So now as we go down the group, what happens generally? Atomic size increases. But here what happens, from boron, aluminium atomic size is increasing, right? Then what happens from aluminium, atomic size is decreasing, gallium, right? Then again from gallium, atomic size increases, atomic size increases, gallium to indium, and then indium to thallium. Okay, the reason behind this is what, that we are adding a extra shell into this energy shell, right? Extra energy shell into this, and at the same time we have weak screening effect of d orbital also here. So general trend, if you see, which is given in the book, there are many different factors involved here, right? So what we can say, the atomic radius of these elements does not follow a regular pattern. Okay, it increases from boron to aluminium and then decreases and then increases, right? It increases from boron to aluminium, right? Decreases from aluminium to gallium and then increases, right? So we don't have a regular pattern here. You see here, the another thing you have to take care of, that here the difference is too much. Too much means when you compare the difference here and when you compare the difference here, right? So here you see the difference is almost little bit lesser than the twice of this value. And when you have difference like this 8 or 3, so since it is in picometer, so this difference is very small actually, right? So that's why in this group size has a role, but the regular trend we don't get over here because of these atomic radius. We we have difference here, but since the value given is in picometer, right? Picometer this value is given, so whatever the difference we have, the difference is not that large, it is very small difference we have, right? On the basis of this only, if you see the order of first ionization energy of these elements, okay, so I'll write down in short now. Boron will have maximum, and aluminium and gallium has almost equal value of first ionization energy. Then gallium is more than to that of indium, which is more than to that of thallium. So that is what you have to keep in mind here, that it does not follow a regular trend. Okay, we don't have only size factor here, there are other more factors which are involved. So this data you have got, or I have given you with the value of ionization energy, the factual thing, right? So this is the order follows for ionization energy. Now on the basis of this, if you try to write down the electropositive character, right, tendency to lose electron, okay, so it is increases from boron to aluminium as size increases, then decreases from aluminium to thallium. This is the electropositive character we have. Yeah, it will affect. Okay, but then again, in inorganic chemistry, the order or the trend that is given, it is based on the fact which is dominating all other factors. Okay, so it's not like in one case we are having only one kind of effect. Okay, we can have two three factors given, right? So that's why, and in the book the order is given, it is based on the factors which is dominating over there. Okay, in inorganic chemistry actually we have fact first, and then we try to explain those facts with the best possible way, and what we say that this factor is dominating over there. So that's why you have to memorize this thing, that where you have to think what factor is dominating when. That's what you have to keep in mind. Size obviously will affect the properties, other properties also. But then we have to see, suppose we are looking at the stability of carbonates, then we have to see what all other factors are involved there, like the Fezan's rule, thermal, like the bond dissociation energy and all. So size does have an effect, right? But what other effects are, that also we have to consider. And depending on that, we'll give the order. But here, that's why here what happens, like I said, that this factor, because of this factor, the order is this. It does not mean that only that factor is there. It means that that particular factor is dominating. That's why we are discussing about that factor. It's just that thing. Okay, so electropositive character is this. Now you see the general electronic configuration is NH2 NP1. So its possible oxidation state is what? It can have +1 or +3. When it loses one electron from here, it is +1. When it loses all these three electrons, it is +3. So generally here also what happens, write down the next thing, the tendency to form +3 oxidation state decreases down the group. The tendency to form +3 oxidation state decreases down the group, and that of +1 oxidation state increases down the group. Increases down the group. Okay. Reason is same, that inert pair effect also we can explain with inert pair effect here. Right. Next, write down reactivity towards air. Okay. So write down the next thing here, which is reactivity towards air. Write down elements of group 13 forms, elements of group 13 reacts with air and forms oxides of M2O3 type. M2O3 type. Right on next line. Gallium and indium are not affected by air, are not affected by air. Next line. Thallium forms an oxide layer on its surface, and that is why and that is why it is preserved under oil, and that is why it is preserved under oil. Next line. Aluminium also forms a layer of oxide on its surface. A layer of oxides on its surface. Okay. You see the reaction boron reacts with O2 at around 700 degrees Celsius. It forms B2O3, right? So other oxides, if I write down, it is B2O3, then Al2O3, then we have gallium Ga2O3, In2O3, and Tl2O3 type of oxide. Now this oxide, it is acidic. Acidic nature decreases actually down the group. These two are amphoteric, and these two are basic in nature. The reason behind this compound to be acidic is right down here. Due to its small size, it has high positive charge density. It has high positive charge density, and hence it pulls electron pair from H2O. It pulls electron pair from H2O and facilitate and facilitate the removal of H plus. The removal of H plus. Right? That's why it is acidic in nature. Okay. As we go down the group, size increases, so positive charge density decreases. Right. So that is not possible over there. Okay. Right on in this only. Next line. These elements also forms oxides of hydroxides of MOH whole 3 type. MOH whole 3 type. These elements also forms hydroxides of MOH whole 3 type, and the acidity of these hydrides these hydrides also decreases as we go down the group. Also decreases as we go down the group. Okay, so the first one is acidic. Again, this is acidic. These two amphoteric. Sorry, oh, by mistake, I've written here. This is acidic. These two amphoteric, and the last two are basic. Right? Again, in this one, you see BOH whole thrice is, again you see it is electron deficient. The structure of BOH whole thrice is like this, electron deficient. And the H2O molecule you have, in which oxygen has lone pair of electron, and this boron here has one vacant p orbital, right? So this lone pair of electron, it donates to this vacant p orbital of boron, and the molecule we get here like this. We have H O H B and OH group. This boron has negative, this oxygen has positive sign. Now finally from this what happens, H plus comes out. Any one of these H plus loses one pair of electron here, and we'll get what? BOH minus plus H plus. And that is how this acid, this BOH whole thrice is acidic in nature. Removal of H plus takes place there. Okay. Next, you write down the next trend, which is nothing but electronegativity. Write down, write down. As we go down the group, the electronegativity first decreases from boron to aluminium. Electronegativity first decreases from boron to aluminium and then increases marginally from aluminium to thallium, right? This is again irregular trend we have, so again it is important. Explanation you see here, it is because of again irregularities in atomic size. So write down the reason behind this. Due to irregularity in atomic size, due to irregularities in atomic size, the force of attraction between the nucleus and electrons, the force of attraction between the nucleus and electrons decreases as size increases, and hence electronegativity decreases. The force of attraction between nucleus and electron decreases as size increases, and hence electronegativity decreases. So this is the reason for boron to aluminium. Okay, now next you write down, as the size, next line, as the size increases, the effective nuclear charge also increases, right? As the size increases, effective nuclear charge also increases due to presence of fully filled D and F orbital D and F orbital present in between the valence shell electrons and the noble gas core. Present between the valence shell electron and noble gas core. The force of attraction between nucleus and the valence electron increases. The force of attraction between nucleus and the valence electron increases, and hence electronegativity increases. Electronegativity increases from aluminium to thallium. Next, you write down electropositive or metallic character. Last one for today. Electropositive. See, the reason that I have given you, it is the same thing that we have discussed so far. Okay, that's why I'm not explaining it. When you read it out, you will understand. Electropositive character, or we also call it as metallic character. Metallic character. So write down in this, as we go down the group, electropositive character increases from boron to aluminium, and then decreases from aluminium to thallium. Increases and then decreases. Reason is also same. The reason that I have given you just now. Write down the explanation in this. Due to increase in atomic size, the ionization enthalpy from boron to aluminium decreases, and hence electropositive character increases. Right? So what we can say, size increases, ionization energy decreases, electropositive character increases. So with this, what we can conclude, that aluminium is a good metal, or better metal you can say. Aluminium is a metal, and metal conduct electricity. Conduct electricity. Since you see boron, the ionization enthalpy, or if I write down the first three ionization enthalpy, ionization enthalpy of boron is high, and hence it is a non-metal. Hence boron is non-metal, bad conductor of electricity. Right? Aluminium is a metal, boron is a non-metal. Now again you see it decreases from aluminium to thallium. So write down next line, the next point, the last point here. The gallium, indium, and thallium, sorry, it is thallium, are less likely to lose electrons due to poor shielding effect, are less likely to lose electron due to poor shielding effect, and hence less electropositive. Right? Due to poor shielding effect of DNF orbital, and hence less electropositive. Okay, so the best metal in this group is what? Aluminium. That is what you have to memorize. Boron is a non-metal, aluminium is a metal, and all other elements has very less tendency to lose electrons because of poor shielding effect of D and F orbit. So this is it. We have discussed few trends, few are left that we'll discuss in next class, and then we'll move on to the revision part. Fine, understood. Okay, can we wind up the class here? Tell me, when can we have class in the Saturday? If school is not there, I think morning will be better. Okay, so will you prefer online or offline? Friday morning will be fine. Friday morning. Friday morning online will be fine. Okay, fine. Okay, so let me check with my schedule. Most probably we'll have class in Friday morning. Online it will be. Okay, but I'll let you know tomorrow. Okay, thank you all. Thanks for joining. Do read NCRT, okay? Okay, bye. Take care.